Hi students, today let's discuss about the magnetic effect of electric current. We will cover the important topics as a quick revision for exams. Okay, so the magnetic effect of current was first discovered by Oersted in 1820. Oersted found out that the conductor carrying current was able to deflect a compass needle. Now we know that the compass needle is also a magnet, and the magnet can be deflected only by a magnetic field. So he concluded that current flowing in a conductor or wire gives rise to a magnetic field around it. Okay, so we can see this diagram here, circuit diagram here. This is basically to demonstrate the magnetic effect of a current. Now see in the figure 1 you see we have a copper conductor which is connected to a battery and the switch is off, and we have kept a compass near to the copper wire. Now as soon as we put on the switch, the current starts flowing in the circuit. So when the current flows through this copper wire, we see there is a deflection in the compass needle. So this is happening when the current is flowing in the circuit. So when there was no current, the compass needle was aligned to north-south direction. As soon as the current started flowing, the compass needle got deflected. So this shows that when the current is present in the circuit, there is a magnetic field around it. Okay. Okay, now see in this diagram, we have a conductor AB which is connected to a battery. So now you can see the current I is flowing through the circuit and the current is flowing in the upward direction. And we can see the direction of the magnetic field which is being generated. So this we can understand by this diagram. And the Maxwell right hand rule gives us the idea of how the magnetic fields are formed depending upon the direction of the current. Now suppose if you are holding this conductor AB in your hand, in your right hand, and the thumb is pointing towards the direction of the current. So when the thumb is pointing towards the direction of the current, the other fingers, they are showing you the direction of the magnetic field which is being generated. So now see in this case, when the current is moving upwards, the direction of the magnetic field is anti-clockwise. So the direction in which the fingers encircle the wire gives us the direction of the magnetic field. The same thing can be understood by the Maxwell corkscrew rule. Next is the magnetic field lines due to circular loop carrying current. Now here you see we have connected a circular loop to a battery and a current I is flowing through the circular loop. Now we can see how the magnetic field is being formed, which is visible on the cardboard. Now this lines are visible because this cardboard contains lot of iron filings which are spread on this cardboard, and as the current flows, this magnetic field is generated and the irons are getting aligned to the direction of the magnetic field. So we get a clear picture how the iron filings are arranging themselves as per the magnetic field. So basically see, this diagram tells us that when current flows through a circular loop, then we get a different kind of arrangement of the magnetic lines, the magnetic field lines. Okay. Now the strength of the magnetic field which is generated will depend upon the number of loops we have. So this diagram shows you a single loop. So as we go on increasing the loop, the strength of the magnetic field will go on increasing. Now the magnetic field strength also depends upon the amount of current which is flowing through the circuit. As we increase the current, the strength of the magnetic field also increases. And if we increase the radius of this loop, the magnetic field decreases. So the smaller the loop, the stronger will be the magnetic field generated. Okay, now let's see how to find out the direction of the magnetic field lines in a circular loop which is conducting a current. So for circular loop carrying currents, we use the clock face rule. Now we have to understand one thing. A current carrying circular loop behaves like a thin disk magnet. Okay. So now one face of this disk magnet is north pole and the other face will be the south pole. The north or the south pole can be determined by this clock face rule. Okay. So now if the current flows in the clockwise direction, then the face will be south pole. And if the current flows in the anti-clockwise direction, the face will be the north pole. So you can see in this diagram also. Here the current is flowing through this loop. So the direction of current is clockwise. When the direction of current is clockwise, we have this south pole being generated. Okay, and when the direction of current is anti-clockwise, we have this north pole which is being generated. So since this loop behaves like a thin magnetic disk, the front face, if we find that the front face is the south pole, then the back side of that will be the north pole. Now let's discuss the magnetic field due to a solenoid. So this is important. So basically a solenoid is a long coil containing a large number of closed turns of insulated copper wire. See here you can see this round kind of thing in the center, that is basically the coil. Now this coil is connected to a battery and the current is flowing through it. So this current is flowing through this. As the current flows, this magnetic field is generated. You can see the magnetic field lines here, and this is the solenoid which is the central part. Now if you notice at the center, the lines are going in parallel to each other. So this shows that the magnetic field due to a current carrying solenoid is uniform at the center. Now this solenoid is basically behaving like a bar magnet. So magnetic field due to current carrying solenoid is similar to a bar magnet. The magnetic field inside the current carrying solenoid is uniform. So one end of the solenoid acts as a north pole and the other acts as a south pole. So you can see the south pole here and we have the north pole here. Okay. So now the magnetic field which is produced inside the solenoid can be used to magnetize magnetic material like soft iron. So solenoids are used to make electromagnets. So we can make a magnet using a solenoid. See the magnetic field which is generated in this solenoid is very strong. So this can magnetize. If you put a soft iron bar inside this solenoid, so due to this magnetic field which is generating around the solenoid, this will magnetize the iron bar which is put inside this coil. So basically the electromagnets are generated using this solenoid. Now the strength of the magnetic field produced by the solenoid depends upon the number of turns in the solenoid. So the more number of turns, the stronger will be the magnetic field generated, and the strength of the current also decides the strength of the magnetic field. So if we have a higher current flowing through that circuit, the magnetic field will be stronger. And the nature of the core material used is also important here. So when we use a soft iron core in a solenoid, it produces the strongest magnetism. That means if we put a soft iron core inside this coil of the solenoid, it produces a very strong magnet or electromagnet. So now you can see from this diagram, the strength of the magnetic field is very strong at the core of the solenoid, at the central part of the solenoid. So solenoids can generate very strong magnetic field, and hence they are used for the production of electromagnets. Now what are electromagnets? Electromagnets are basically magnets which are produced due to the current flowing through a circuit, and the material which has to be magnetized is put inside the coil or the solenoid. So we see electric current can be used for making temporary magnets, and these temporary magnets are called electromagnets. So electromagnets work on the principle of magnetic effect of current. So here this circuit diagram shows you a electromagnet. So you can see the coil, and you have a soft iron core inside this coil, this part, and this is the power source, and the current is flowing through this circuit. So this soft iron core which is inside the coil, this will get magnetized. Now this magnetism is dependent on the current which is flowing through the solenoid. As soon as we switch off the current, this soft iron core will become a normal iron piece. It will lose its magnetism. So magnetic effect of the electromagnet is available when the current is flowing through the circuit. So the electromagnet loses its magnetism when the current is turned off. So now we have this flexibility, we can control this behavior of this soft iron core. Whenever we want, we can make it a magnet, and whenever we want, we can bring it to its normal state. Okay. Another important point is the U-shaped electromagnets are strong magnets compared to bar magnets. So U-shaped magnets are strong magnets compared to bar magnets. So this is dependent upon the length of the air gap between the poles. So now see, we have a bar magnet here. This is the south pole, this is the north pole. So the gap between this north and south pole is quite large. Now if you see this U-type magnet, you can see the north pole and south pole are very near to each other. So there is less gap between the poles, so it creates a strong magnet. Now we can say that electromagnets are better than the permanent magnet, because electromagnet can produce very strong magnetic field, and the strength of the magnetic field can be increased or decreased by increasing or decreasing the current, and also by changing the number of turns of the coil. So there is a flexibility. As per the requirement, we can produce a very strong magnet, we can produce a medium kind of magnet, but that is not possible with the bar magnet. So let us see the difference between a bar magnet and an electromagnet. See, bar magnet is a permanent magnet, but an electromagnet is a temporary magnet. Its magnetism can be switched on and off. So when the current is flowing, it will behave like a magnet, and when the current is put off, the magnetism vanishes. Now a permanent magnet produces a comparatively weak force of attraction. That is because the gap between the poles are very high compared to a U-shaped magnet, An electromagnet can produce very strong magnetic force. It can produce a very strong magnetic force, we know that. The strength of permanent magnet cannot be changed, but the strength of an electromagnet can be changed by changing the number of turns of the coil or by changing the current flowing through it. The north pole and the south pole of a permanent magnet is fixed. We cannot do anything here. But the polarity of the electromagnet can be changed by changing the direction of the current in the coil. So when the current flows in the upward direction, we have seen the magnetic field will be moving in the anti-clock direction, and when the current flows in the downward direction, the magnetic field will be moving in the clockwise direction. So the polarity of the magnetic field can be reversed by reversing the flow of current. Okay guys, so now this is the end of the session. So in the next session we will be discussing about the Fleming's left hand rule, right hand rule, the concept of motor and generator. Okay students, wait for the next video. If you like this session, please share and subscribe. Thank you.